All right, so we're going to go through chapter 6.9 here, and we're going to do homework number 17, 23, and 33. So really just grabbing one from each of the different sections within this homework. So the first one here, we want to write a cubic function, and we want to pass through these given points. So as soon as I am told I have a cubic function, as long as I have 4 or more points, I know I can determine what this graph will be based on that information. So basically what I'm going to do is I'm going to set up a giant matrix for this thing. So the giant matrix is just going to look like my general form for a cubic, which is ax to the third plus, now here I would get bx squared plus cx plus d equals my y value. And now I may, have some sort of information here which is extra, which is like 0, 0. So I know, for example, that my d value is going to be 0 here. But if we didn't know those things, another point that we could kind of highlight is that here we have -1, 0, -2, 0, and 0, 0. So each of these factors is giving me a 0. So when we're looking at this problem, I could also approach it that way. So when we're looking at this, I'll highlight the way that we can always just brute force our way through, and then I'll talk about how I personally would do this problem. So to do this, we would take each of these points. So I'm just going to highlight one of them here because I don't particularly want to go through and do this entire thing, but actually let's do a slightly more interesting one. Let's do this. So I'm just going to highlight one example. So for each of these, we're able to plug them in for our x and our y values, and we'll get some number of a's, some number of b's, some number of c's, some number of d's equals y, right? And our y value here is going to be -3. So plugging this in, it would look like this. Hopefully I don't start there. I'm going to run out of space. So a, and then I have my 1 value to the third plus b times my x value again squared plus c plus d equals -3. Oops. So in this problem here, I'd get a plus b plus c plus d equals -3. And that would be for this point. Now again, I don't want to do all of these things, but I can go through and let's do, I don't know, this one, for example, slightly more interesting. So here I'm going to get a times and my x value here to the third plus b times, oops, my x value squared plus c times that x value plus d equals, now here it's going to be 0 because my y value is 0. And so as I go through and evaluate this, this will give me -8a plus 4b minus 2c plus d equals 0. So here's just one of my equations. Here's another one of my equations. And I would get 2 more of these things, and I would enter it into a matrix. So this matrix is going to have 1, 2, 3, 4, 5 columns, and I have 4 rows of information. So I've got a 4 by 5 matrix that I would then go put into reduced row echelon form, and I could solve for it that way. So this is one way of solving this problem. And we can always solve these problems like this. So can always go back to that. But this one I see in particular is giving me a 0, a 0, a 0, and then some point. So if I am given 3 zeros, I'm able to use those zeros as intercepts and turn them back into factors. So I'm going to turn this back into x plus 1. Then I'm going to turn this into x plus 2. And here, I don't really need to write this out as x plus 0, but I'll do it just to keep uniform. And I'm going to say equals my y value, whoops. And I don't know what my a value is for this. So again, each of these being intercepts, being zeros, I can represent them as their factors, and it's going to equal the y value. So then if I choose my point, so this 1, -3, and plug that in here, I'd be able to solve for my a value. So to do so, it would look like a times, and here I'm going to get 1 plus 1. Here I get 1 plus 2. Here I get 1 equals, now here's -3. So now I'm going to just do some multiplication here. So this is a times 2 times 3 equals -3. Oops. And now from here, I'm just going to say 6a equals -3. So divide by 6. And a equals -1/2. So as my final equation here, I would get -1/2 x plus 1, x plus 2, x, and typically this x would just be written out in front here, but I don't really particularly care where you write it, and then equals y. So this would be the cubic function whose graph passes through those points. That's what we're looking for. So this is one way of doing it. Another way of doing it is, again, to go through, do reduced row echelon form in my matrix, and then it's going to spit out in standard form. So if I multiplied all these things out, then I would get back to what this one would look like. So intercept form versus this would spit out in standard form. Any questions here? Perfect. Let's look at this one here. So we want to show that the nth order differences for this given function of degree n are non-zero and constant. So this is, again, just like a show problem. So how do I show this thing? So in order to do this, I want to plug in all of my different values. So I'm going to typically just do like 7 of these things. So I'd want to do f of 1, f of 2, f of 3, etc., etc. Typically 5 or 6 is enough, but depending on like what the function is, if it's a higher degree function, then we'll have to show higher order differences. And now I want to figure out what my f1 value is. So I'm plugging 1 into this equation. So when I'm looking at problems like this, every time I do this, I'm just evaluating what these points are, and then I'm saying, okay, take the bigger one in terms of like counting up, like I'm going to take my f7 and subtract off f6 and see what that gives me. And I do this sort of like triangle down method here. So I'm going to evaluate for this thing. So let's see, we got x squared minus 3x, and we got plus 7. And when I plug in 1, I get 7. When I plug in 2, I get 5. Plug in 3, I get 5. Plug in, oopsie, that was not what I wanted. I want starting with f1, not f0. So first one I plug in, I get 5. Here I get 5. Here I get 7. Here I get 11, 17, 25, 35. So again, just plugging in these values into this equation. So plug in a 1, spits out a 5. Plug in a 2, spits out a 5. So now I'm going to take these and I'm going to do 35 minus 25. I'm going to do 25 minus 17, 17 minus 11, 11 minus 7, 7 minus 5, and 5 minus 5 here. So as I do this, this will give me 10. Here I got 8, 6, 4, 2, and 0. And now I'm going to do 10 minus 8. So I'm going to do it again now, finding what order differences. So the row in yellow are my first order differences. And now I'm going to my second order differences. Note that this is a second degree function, so it should have second order differences. So 10 minus 8, 2, 2, 2, 2, 2. Cool. Now we have our second order differences that are all non-zero and constant. So here we have shown that they have nth order, nth being 2 here, differences for this function. Any questions here? So like on a test, this is kind of like what I'd be looking for. Perfect.
How far do you know how to go out? So like you went to 7.
Yeah, so I know that for all the ones we're doing, 7 is enough. If you were doing like 12th order differences, for example, you'd have to go out much further. But for everything that we're doing, if you just do 7, you'll be fine.
Okay.
Yeah.
Cool.
So we're never going to go past like 3rd order, 4th order differences. It's just like too much, and it's like to what gain. You know, it doesn't really do us that much more good to see, okay, I can do this 11 more times or whatever nonsense like that. Good question. So here we're going to use finite differences and a system of equations to find this polynomial function. So we're looking at this one here, we'll do 33. The first thing I want to figure out is what nth order differences this has. So I don't really know as of right now. So what I'm going to be doing is I'm doing the same thing that I just did, which is I'm going to take my f of x values, right? When I plug in 1, it spits out 17. Plug in 2, spits out 28. Plug in 3, spits out 33, etc., etc. And I'm going to do my finite order difference test here. So I'm going to be doing 12 minus 25, which is negative 13. We'll do 25, oopsie, 25 minus 32 here, get negative 7. 32 minus 33 is negative 1. Then we get 33 minus 28. And we get 28 minus 17. And now I'm going to go through and do it again, trying to find those finite order differences here. So 13 minus a negative 12 is going to be addition here. So it's going to be negative 6. 7 minus a negative 1 gives me negative 6. 1 minus 5 gives me negative 6. 5 minus 11 gives me negative 6. So here were my first order differences. So if it was this, it would be telling me it's a linear graph. And here, this is my second order. And since my second order are all constant non-zero, this is what degree function this is. So this is a second degree function. And the reason that that's helpful is now I know what sort of standard form I want to plug this thing into. So I know I can do, grab another color here, ax squared plus bx plus c equals my y value. And I would just pick 3 points. So let's say I was just doing the 117, the 228, and the 333. For example, I would take each of those, plug them in, I would get an A, B, C equals some number, and then I would set up my matrix from there. Does anybody want to see that done out? It's the same things we've talked about and have done before, but if people want to see it, I'll do it. We're good? Cool. All right, so again, if you wanted to continue solving this the rest of the way, take each of these x's and plug them into this equation and plug in your y, and it will give you an equation with a, b, and c in it. You'll do that 3 times, so you'll have 3 equations with a, b, and c. You turn that into your matrix. So my matrix here is going to be a 3 by 4. And then, whoops, from there, I'm going to do reduced row echelon form to get my a, b, and c values, and then I'm done. So once I've solved that, I've solved my problem. I've found whatever the polynomial function that fits this data is.